Hello class. So on this video, we're going to continue on section 6.6, talking about convolutions of functions. Right? In the previous video, we defined what f star g, or the convolution of f and g is. Right? We went over some properties of the convolution. Right? And then we gave a theorem, which is the most important thing for us. So I talked a little bit about other applications in which convolutions arise. But again, for our purposes, this is the important thing of convolutions. It allows us to take the Laplace inverse of products of functions of S and write it almost as a product, but not as a product entirely, but as f star g. Right. So let's use this. Right? So let's try to find the Laplace inverse of a over s squared times s squared plus a squared. So first, notice that we can think of this expression as the product of two functions of s, which we know what which we know the Laplace inverse of. So we know what function is mapped by the Laplace transform to them. Okay, so it's really complicated to talk about this in words. So let me just write it out. Okay. So what I'm trying to say is that the Laplace inverse of this is the same as the Laplace inverse of, let's write it as 1 over s squared times, and this is just regular times, a over s squared plus a squared. So you can think of this, we want to take the Laplace inverse of a product of functions of s. So as long as you know what function is mapped to 1 over s squared and what function is mapped to a over s squared plus a squared by the Laplace transform, then you know what this is. And we know what those functions are. Right? We know that the Laplace transform of t is precisely 1 over s squared. And then this one, I believe, is cosine, or no, it's sine. But let's double check, though. Yep, k over s squared plus k squared. Yeah, so this one's sine. Okay, so Laplace inverse of sine, in this case, at, is precisely equal to a over s squared plus a squared. Right? So this satisfies what we needed. We're trying to take the Laplace inverse of a product of functions of s, and we know what functions of t are mapped to these functions of s by the Laplace transform. So we can just use theorem 1. So by definition, the Laplace inverse of this product is just going to be the convolution of t and sine of at. Right, so, and that's how we use this theorem. Right, this is, by definition, the convolution of t with sine of at. And here, since we're using t as the independent variable, right, then you can think of this, you can just remember the names are just dummies. Right? So the fact that we're using variables here doesn't matter because they're just dummy variables. Right? So when you actually go ahead and complete the convolution, you can just replace the t with the tau. Just like we did in the previous example. So let's simplify this. By definition, this is going to be the integral from 0 to t of what? We have a choice where we put the tau. So let's say we put the tau on t because it's simpler. So let's write this as sine of a tau, sorry, where we put the t, times t minus tau, d tau. And notice this is exactly the same thing we did here. We had functions of t, right? It was just replace everything with tau, right? So using this definition here. And again, by commutativity, you have a choice where you put the t minus tau, right? So for example, this is exactly the same thing as saying sine of, so a times, let me use brackets here, sine of a times t minus tau. So now I'm putting the t minus tau in the sine function times t without the t minus tau. Oh, sorry, times tau. Right, so again, it doesn't matter where you put the t minus tau because of commutativity. And now you could compute what this integral is. You're going to have to do integration by parts just once, right? So I won't finish it. You can do it as an exercise, but then you can solve exactly what your function is. Right, so now you see the power, or one of the reasons why the convolution is important for us. It gives us the power to take the Laplace inverse of products of functions of S. Now, let's use it to find the solution to an initial value problem. So find a solution for y double prime plus 4y equals g of t. We're not given what g of t is. What we're going to assume is that the Laplace transform of g exists, because we're going to be taking the Laplace transform, right? Where y of 0 equals 3 and y prime of 0 equals -1. Okay. So let's do our work. We know how to do this. Take the Laplace transform of both sides. We get s squared, big Y of s, minus s times y of 0, sorry, which is 3, minus y prime of 0, which is -1. Right, that's just the Laplace transform of y double prime, plus 4 times the Laplace transform of y equals the Laplace transform of g. We don't know what it is, so let's just write it as g of s. And again, here we're assuming that we can actually compute the Laplace transform of g of t. There's just any arbitrary function whose Laplace transform exists. So let me write that. Okay. Now, as always, let's just solve for y of s, big Y of s. So let's see. We have s squared plus 4. Oops. So s squared plus 4, big Y of s. And then what do we have left over? Minus 3s plus 1. Yep. Equals g of s. Now let's divide both sides. Well, add 3s plus 1 to both sides, or subtract 1. So let's do that step. It's kind of obvious, but let's just write it out. There's g of s plus 3s minus 1. We're almost done. Let's just divide everything by s squared plus 4. Okay. Now, we want to find what big Y of s is, so let's take the Laplace inverse of both sides. Sorry, we want to find what y of t is. Right? So let's take the Laplace inverse of both sides. So y of t is equal to the Laplace inverse of y of s. Right? And then by linearity, we're just going to separate this. It's going to be equal to the Laplace inverse of, let me write it like this, g of s times 1 over s squared plus 4, plus, by linearity, 3 times the Laplace inverse of s over s squared plus 4. And then again, by linearity, minus the Laplace inverse of 1 over s squared plus 4. Let's just calculate each term separately. Now let's do this term, let's leave it for last. Okay, so let's do the other ones. So this one is very easy. It's just 3, this one I think I remember. I think this is 3 cosine of 2t, because k is equal to 2. Now for the other one here, we are going to have to do a little bit of work. It's almost in the right form, but what we have to do is multiply by 2 over 2, like we've done before. So let's write it as the negative or plus inverse of 2 over 2 s squared plus 4. Let's move the 1/2 outside, so we get negative 1/2 plus inverse of 2 over s squared plus 4. And this is precisely sine of 2t. Oops, that's a weird looking 2. Okay. Now, so we have those two terms, right? We have this term, we have this term. Let's try to compute this last term. Right, so let's do, so let me make some space here. So let me separate things. Oops. Yeah, so let's do the Laplace inverse of g of s, big G of s times 1 over s squared plus 4. Now, we already did part of the work here. Well, first of all, notice this is a product of functions of s. So potentially we can write this as a convolution of functions. We just have to decide what they are. Well, g of s, we know what function is mapped to it. Right? By definition, g of s is the Laplace transform of little g of t. Right? So this, oops, let me use another color. Right, so we know that the Laplace transform by definition, right, of g of t equals g of s. And here we already did the work, right? The Laplace transform of 1/2 sine of 2t is precisely equal to this. So by definition, this Laplace inverse, okay, let me use a different color. So the Laplace inverse of g of s times 1 over s squared plus 4, by definition, or using theorem 1 is really what we're using, is equal to the convolution of g of t with 1/2 sine of 2t. And again, we can write this as an integral. Doesn't matter where you put the t minus tau. Let's just write this as the integral from 0 to t of, so let's put it inside the g. So g of t minus tau times 1/2 sine of 2 tau d tau. So what's the final answer? Combining everything, y of t is equal to this thing, this convolution, so the integral from 0 to t of, and just for sake of demonstration, I'm just going to write the t minus tau on the other function, g of tau times 1/2 sine of 2, let me use brackets, 2 times t minus tau d tau. And again, we can do this because it's commutative. It doesn't matter where you put the t minus tau. Okay. Plus the 3 cosine 2t and then minus 1/2 sine 2t. So what's the point of this example? Well, the point is the Laplace transform. The convolution allows us to find solutions to at least, just based on this example, to second order linear ODEs with constant coefficients, right, in which our function g of t is not specified. Meaning that we get a general formula for the solution, and then if we want to find what the solution is for a particular g of t, we can just plug that in here and calculate what this integral is. So mathematicians love doing this, right? Giving you a general formula for something, just like mathematicians found the general formula for the roots of a quadratic polynomial. They could give you, well, for this particular polynomial, the roots are -1 and 2. Instead, they say, in general, given this general polynomial, this is a general formula for the roots. So it's something similar going on here. Given a general function g of t, which we don't know specifically what it is, with the only assumption that its Laplace transform exists, we have a general solution for this ODE. Right? And it's given by this equation. You want to know what it is for a specific function g of t, plug it into this integral, calculate that integral, and you get the specific solution. And then more generally, this works if we want to take to find the general solution of any, at least, second order linear ODE with constant coefficients, where the constant coefficients are arbitrary. Right? So in this case, I gave you the coefficients where, so they were 1, 0, and 4. 0 because there's 0 times y prime. Right? So we can write the general solution using this method for an initial value problem of the form a y double prime plus b y prime plus c equals g of t with initial conditions, whatever they are. Y of 0 equals, let's say, let's give them names. What should we give? Oh yeah, let's give them y naught, and then y prime of 0 equals y1. So you can actually find the general solution for this ODE only using the assumption that g of t, with the only assumption needed being that g of t has a Laplace transform. Right? So I'm not going to do it because I don't want you to memorize like a formula. Okay, given this ODE, this is what I get. I do want you to know how to do it, right? Which is why I set it up here and we went over the whole process. So again, two very powerful reasons to introduce the convolution. It allows us to find the Laplace inverse of products of functions of S, and it allows us to write more general formulas for solutions to initial value problems. And as I said, this is the last section for the exam. Right? So in the next videos, as I mentioned, I'm going to be covering just selected topics that I find. The videos are probably going to be shorter unless the material is a little bit hard and I have to explain a lot. You're not going to be required to watch them. I'm just going to put it as bonus content. That's probably where I'm going to name the module. But you're welcome to see it. I'll upload it to my YouTube page anyways, to my YouTube channel. So if you ever see it later in future classes, which I'm sure most of you will, you can just say, hey, if I need a review, I'm going to go watch this video that I know that because I remember I saw this somewhere in ODE. So I'm going to go watch this review. Okay? But this is the end for the material for the exam. Right? So we're going to be covering chapter 4 and then chapter 6 from section 1 all the way to section 6. Right? So I'll send a message with all this information. But for now, in terms of material, you can think, okay, we're done. In terms of material, I actually have to learn.